sponsored by the CEG department of the University of Minnesota, and it also serves as the 2023 EMI Engineering Mechanics Institute Elasticity Committee Distinguished Lecturer. In this vein, it is my great pleasure to introduce our speaker, Roberto Ballarini. Dr. Ballarini is a Thomas and Laura Sue Professor and Chair of the Department of Civil and Environmental Engineering at the University of Houston. His multidisciplinary research focuses on the development and application of theoretical, computational, and experimental techniques to characterize the response of materials to mechanical, thermal, and environmental loads. He is particularly interested in formulating models for characterizing fatigue and fracture of materials and structures. Ballarini's research has been applied to problems arising in civil engineering, mechanical and aerospace engineering, material science, biological tissues, and prosthetic design. He has published more than 120 papers in the referee journals, including Science and Nature, and several of his research projects have been featured in popular press, including New York Times, American Scientist, Business Week, and Financial Times. Ballarini is a distinguished member of ASCE, fellow of the Engineering Mechanics Institute, EMI of ASCE, and a fellow of ASME. He also served as the president of the EMI and the editor of the ASCE Journal of Engineering Mechanics. He is a 2019 recipient of the Raymond Mindley Medal in recognition of his achievements or in contributions to applied solid mechanics. And then for the more junior, I would say less senior part of the audience, Roberto was our colleague in this department from 2006 to 2014. So with this, please join me in welcoming Roberto.
Thank you, Boyan. Anyway, thank you, Boyan, for the introduction. It's great to be here, so I'll just say two things. One is about just the department. I sorely miss this department. It's a great department. I miss all my colleagues, and it's great to be back. It's just amazing. I was telling Kathy that it's been almost 9 years since I left. And in fact, I've been in Houston for longer than I was in Minneapolis. But I'm glad to see all, especially the younger faculty that have been hired. You guys have made some really, really good hires. I've been following the department since I left. And again, thank you for having me back. This is also a lecture, I guess, for the EMI Elasticity Committee. I want to shout out to them also. Just a little bit of history. I think I probably violated some rule. I've been on this committee for about 38 years. I'm not sure whether I'm supposed to be on it for this long, but to give you an idea of how this committee has really evolved and really has become even more vibrant, when I graduated, I think I was on the committee. My classmate Greg Miller was. My advisor was ex officio Leon Kier. I don't remember anybody else being on the committee. We were actually talking about whether it should be disbanded. But it did not happen, and I think it's grown over the years. Now it's a very vibrant committee with really good leadership, especially some of the up-and-coming stars in elasticity, and they're working on problems because elasticity is a very important topic, of course, and it's also it's kind of reemerging with all the problems in biology, problems in imaging, also cloaking, all sorts of things that are very exciting and making elasticity, again, as relevant as it has been in the last hundreds of years. So with that, what I'm going to talk about today, I've given several lectures in this department. They tend to be, I would say, accessible because they don't have much mathematics or, they're for the general layperson. But today it is an elasticity meeting or elasticity seminar, so it's going to be a little bit more esoteric, but I'll try to make it relevant and make it as understandable as possible. There will be equations, but I don't want you to even look at them. I just put them up there to make sure that you know that some of the solutions that we will be using are available, but it's really not meant. So anyway, I did this work with Johnny Royer Carfagni a few years ago. I haven't presented it much. I thought I'd present it today here to my previous home. Johnny, as some of you know, is a brilliant person. He came to visit me for about 5 months. My wife was still in Minneapolis. We were selling our home, so we just hung around in the evenings and played with elasticity. And then we go out for a beer, perhaps. But he's a very brilliant person, and he wanted to learn a little bit more about cracks and dislocations. So I would give him my notes, and then we would chat, and we came up with this thing. So I'm going to talk about are configurational forces real forces, and I'll describe what they are. If you want to see the details, the paper is a little bit old now. It's quite old, actually, in JMPS, and you could read some of the details if you're interested in these kind of problems. I'll try to summarize them. What is the motivation of this work? Just fun. I'm not sure if it has any practical applications, at least on the continuum scale. But again, it's sort of ontological, perhaps pedagogical, because this idea of configurational forces is a little bit even more abstract than perhaps Newtonian forces, which could also be potentially discussed whether they exist. But let me just start by introducing on both sides this idea that if you have some variations in energies, from your physics, it's kind of like a force times some sort of displacement, right? This would be, let's say, a Newtonian force, if you will, if I push on something. But there's something called a configurational force, perhaps when something moves like a dislocation or a crack tip, where this may be the position of that thing, right? L, maybe the position of a dislocation or a crack tip, and then it moves somehow. So we define this thing so that if we know the energy change, a force, a configurational force, and it's called that only because the configuration is changing. So a little bit of history here, because this is kind of a trash talking people between energy and Newton forces. So if you look at D'Alembert, he writes, forces are obscure and metaphysical beings, capable of nothing but spreading darkness over a science that's clear by itself. Maupertuis, we speak of forces only to conceal our ignorance. Obviously, he's trash talking Newton. An obscure and metaphysical notion, that of a force, Carnot. But then you go back to the other people who think about the other way, like Thomson and Tait. They have a treatise on philosophy, natural philosophy. Every attempt that has been made to supersede them has ended in utter failure. I tend to be liberal, so same thing. It's all the same thing, different clubs, different way of approaching problems. But I do want to kind of reconcile these. So first of all, I'm going to talk about examples, then we'll generalize at the very end. I'll talk about a configurational force associated with a crack tip in an elastic body. The configurational force, what would appear here for fracture mechanics, is the so-called J integral. It's basically an energy release rate, so that the variation in some energy is that thing called J, which is not a Newtonian force, times the variation in the position of the crack tip. But I'm going to show you that in a crack, there is actually a Newtonian force, if you accept a certain assumption that I'll talk about at the end. There's also types of configurational forces which Eshelby actually worked on, which are when a dislocation is moving in a solid state. So you have the movement now, the position of a dislocation, the dislocation moves by some amount, whatever multiplies so that you have a variation in energy is, again, that configurational force. That's called a Peach-Kohler force in a dislocation. I'll start out with some toy models to give you some insights of how these things work. And what I want to show you then is that you could interpret this with some assumption that I'll talk about later, that this actually is a Newtonian force. Okay? And you'll have to, I'll hand wave a little bit perhaps, but I'll show you how I could reconcile the two. So Eshelby, for those who are students especially, or even young faculty, he didn't live in the world of publish or perish. I think he has on the order of maybe 6 papers. Xantippe Markinskov collected his works about a decade ago or so. They're all gems. Really kind of an inspirational figure who really was very good. He did a lot. He was able to do what I call mathematical acrobatics, but he also had tremendous physical insight and understood physics, and he has very, very beautiful works. I read many of them. They're all gems. It's kind of a good example. So what I'm going to start with is actually give credit to a very good colleague of mine who I think was here a year or two ago, Davide Bigoni in Trento, Italy, that's basically pioneered the idea of configurational forces in what I call structural elements, like beams and rods, those kind of things which are discrete. What we did is generalize some of those ideas to what I call the continuum. So, but it actually goes back to some old papers by, if you dig deeply, you always find the Russian had their hands early on in some of these ideas, right? Very, very bright. So it goes back actually to about 1970. Davide, of course, he has the same hairstyle as I do. That's the only thing he copies from me. He's a brilliant guy, and I think he was here as a MTS professor. He's also a very good teacher, by the way. If you're actually a professor and you want to look at some nice YouTube videos that you could use in your class, go to his site. He has some very nice 5-minute presentations of theory and about 10, 15 minutes experiment. And they're very well designed experiments that he uses, including the one that I'm going to show you today. So let's say you're teaching solid mechanics, and this is his handwriting. He's allowed me to use his slides, of course. The idea is you have a beam, right? An elastic beam, not a rigid beam. And you put a load on the end. And then, of course, you have your reaction at the wall. Now, that wall is basically infinitesimally thin, perfectly smooth guide. And you put a force on it. You have your vertical force. You have your bending, your moment at the reaction of the wall. But a student or you will never put a horizontal force, perhaps, right? S. But it turns out that there's something called an Eshelby force or a configurational force. If you think about the fact that not only do you have a degree of freedom, which is the vertical displacement at the point force, F, but you also have the configuration that that beam could slide in or out of that smooth guide. Is that clear? So if you now have, this is the bending energy of the beam, this is the work essentially done by that S force that I introduce. This is the movement of that beam. And the idea is that because the beam is actually bending at that corner, I'm going to do this problem 3 different ways. If you write the energy and you make the energy stationary with respect to that position, this degree of freedom, this part is what we call an Eshelby type force. What this means is, if you actually do that experiment, if you don't hold on with that force S, that beam will slide out of that guide. It'll just slide out. So there's some force, if you will, that wants to drive that configuration change. You could see it from energy very easy. This is basically a problem in undergraduate solid mechanics. So that you sort of have to hold on to it because of the deformation. Of course, if it's rigid, that won't happen. But because you have energy in the system, this will happen. Another way of looking at it, and this is the method that we're going to be using for cracks and dislocations, is to think about this a different way through some equilibrium. So what David has done is, of course, you solve now the problem where you allow these 2 walls to have a gap delta so that you draw that configuration. Then it becomes clear if everything is smooth that you have this Q force, which is this vertical because it's normal to that, there's no friction. But at that corner, that's where everything is happening. You have a reaction R, which is normal to the surface because it's frictionless, but you could decompose that force into a vertical component, horizontal component. You work all that out, then you take the limit as delta goes to 0. You go back to the primitive configuration. The horizontal component does not go away in the limiting process. So you end up with that force again through this kind of procedure. So this is again the Eshelby force, which remains there, which is driving this thing out unless you hold it on the other end. Now, to generalize this is what I would call, allow me this dirty language, I'll call this a perturbation technique, okay? I'm not sure if it's the right word, but I'm perturbing it and going back. I'm going to be using that later with cracks and dislocations. So what David did is he generalized, this is actually not an easy problem of the Elastica. It takes a lot of algebra to solve these kind of problems. So what he did is he generalized this to an inclined smooth guide. And then he analyzes all that, and then he sees again, what is this force S that is in the system? Again, you get the Eshelby type force, but now you get that this force S could either be greater than 0, equal to 0, or less than 0, depending on this angle that it makes at the right end. So as expected, this configuration, unless you provide this kind of force, this will slide down. This configuration, unless you pull the other way, will shoot out like an arrow, and then there is some value when it's equal to 0. And he has the experiments, of course. You don't have to go to school to see these, basically, this physics. You don't worry about the sound. He's just showing, again, I use his experiments. There's no reason to reproduce them. So this is the equilibrium state. This is a perfect guide, smooth guide with rollers. And then he tries to perturb it. Shoot, goes in, right? There's a driving force to go in. That's the Eshelby force that drives the configuration change. And then if he goes the other way, he puts more load on. And this all makes sense without any mathematics, right? This is common sense in a sense. But the idea is what's driving that configuration change? We call those configurational forces. Now, this does have some applications in these discrete systems. This is a beautiful sketch. He does very nice work. I think he made the cover of the Royal Society, I don't know how many times, with some of these experiments and figures that he does. So I don't know if you know how a snake moves forward. It moves forward because of Eshelby force. Why does it squiggle around? Because as it's deforming this elastic energy that's stored in it, and then it releases it, there's a force that drives it forward. There's an energetic force which wants to change the configuration of that snake's position. The only one where there's no force if it's a perfect circle. If that guide is perfectly circular, there is no Eshelby force. But the idea behind this is that you have kind of an arrow launcher without any moving parts, right? You stick something in there, and it'll just shoot something out. It could be like a machine that shoots things out without having all of these other moving parts. But anyway, let's talk now a little bit about the continuum. So inspired by Davide, let's go look to see what is a crack. So if you have a crack in the structure, I'll just focus on a two-dimensional crack of length L, then there's something called the energy release rate where you could derive by looking at the load displacement curve of cracks of different lengths. And then when you go from one state to the other, there's a certain strain energy released. That's called G, the energy release rate, change in potential energy with respect to the configuration change of the crack tip is moving. That G could also be written in terms of an invariant integral of mathematical physics called the J integral, where if you integrate around this path, that thing, whatever it is, don't worry about what it is, that integral is path independent. You get the same value no matter what path you take around that crack tip. And you could show that that energy release rate, which has some intuitive physical meaning, is actually equal to that J integral for the linear elastic. So this is the formula, which is basically, as I said, some variation change in energy. When you have a configuration change, the crack tip is moved. This, by analogy, is a configurational force. So the J integral is a configurational force. Okay? So let's see whether we could reconcile that with some sort of Newtonian force that perhaps we have better intuition about. What I always try to do also is to give credit also to the really early works. So Eshelby was the one who developed these ideas, but if you dig deeper, this idea of these invariants go back all the way to one of the great mathematicians, Emmy Noether, who again never had a faculty position in Germany where she was because of obvious reasons. I think she ended up being at Bryn Mawr College in Pennsylvania for a while. But her work is actually instrumental in many of the advances in physics. And she has Noether's theorem, which basically, in simple words in Wikipedia, every differential symmetry of the action of a physical system has a corresponding conservation law. Physicists start with these symmetries, and then they derive the conservation laws. The action is the integral over time of a Lagrangian function from which the system's behavior could be determined by the principle of least action. All of these ideas like J integral and fracture and others are actually applications of Noether's theorem. Okay, so she was Einstein actually respected her quite a bit, but he made a little faux pas. He said that she was one of the greatest women mathematicians. I think that was a mistake. I think she was one of the greatest mathematicians. Didn't need that word in between. But anyway, so let's look at the crack tip again. So the idea is, how do we use the J integral? So I describe it as this J integral, this driving force to make the crack go forward, is what I call the pain felt by the material ahead of the crack tip. And when the materials, has a certain amount of pain that it could tolerate, J critical, the crack will extend. That is, the driving force overwhelms the material's resistance to crack propagation. That's the fracture toughness. The crack will grow. So again, we defined all these things through fracture. How do you use it? I've used it myself just for classroom exercises. You could do quick and dirty calculations. So this is one of the problems that I worked on years ago, is these seashells, which one of the mechanisms for toughening is basically having cracks grow parallel to each other. If you have a bunch of cracks that are growing parallel to each other on the surface, the material becomes much stronger, becomes much tougher, because the cracks shield each other, they soften the region which they've cracked, so the load gets transferred to the other parts of the structure with a reduced stress concentration. So the model is something like that. If I wanted to get a quick and dirty calculation for what the driving force is for one crack being there versus many cracks, then you have cracks of length C, periodic. You have spacing A. And if you do an energy argument, you could find that the strength of this rod that has all these cracks, if it's an isolated crack, then the strength is inversely proportional to the square root of the crack length, which is the Griffith criteria. Cracks are dangerous. They reduce the strength because C is in the denominator, and if C gets larger, the strength gets lower. However, if you have many cracks close to each other, they essentially soften up that whole region. So if you do the asymptotics, you find that the strength is inversely proportional to the spacing. So when the spacing gets smaller, the strength goes up because the cracks shield each other. If you want to do this very quickly with the J integral, it's a beautiful exercise. I always say in mathematics, when you're stuck, your professor tells you to integrate by parts, right? Whenever you're doing an integral, just integrate by parts. In the fraction mechanics, when you're stuck, you apply the J integral. And so if you do this problem now, a toy problem where you have this stripped spacing of cracks S, crack length A, you apply this crazy integral, don't have to worry about what it is. It's a trivial one-line integral to do, and you immediately get the K, which is the energy release rate, goes as the square root of the spacing. So when the spacing gets smaller, the driving force gets smaller, and the material strength goes high. So again, it's an application of J, but that's not really the point of today's lecture. The other thing I want to talk about before doing the reconciliation between Newtonian and energetic forces is talk about what a dislocation. If you dig deeply, a lot of advances in elasticity were made by Italians, right? That's not surprising, right? That's a joke. But if you go back to Somigliana and Volterra in the Cesaro, they discovered conceptually dislocations way before they were seen in the experiments in the 1950s, perhaps, right? With all the techniques we have to image dislocations. But they're basically imperfections in a solid state. Dislocations could either be sliding type of dislocation or shearing or whatnot, or disclinations. But basically a simple two-dimensional picture is if you do this exercise where you make a cut in an elastic plate, you insert a rigid plate, you bond it together. This was originally stress-free. Now you've opened it up and put sort of a crack in here. It produces a residual stress field here. So this process is equivalent to sticking an extra half plane of atoms in the system. It could either be a sliding type of dislocation like this one, or it could be an opening type of dislocation. But the important thing for today's purposes is that a force is very similar mathematically to a dislocation. The only difference is that if you take a free body diagram around the region where you apply a concentrated force, the traction, the components of traction there are such that when you integrate the effect of all the traction on the free body, it equilibrates the force. So there's a net force there. But that's on any line, though, there's no relative displacement, so that there are single value displacements in the force. A dislocation is a different thing. You have, when you go through a circuit, a relative sliding or opening, so-called Berger's vector. That's what defines a dislocation. However, it's self-equilibrated. There's no net force in this problem. If I integrate the traction around this free body diagram, there's no force. That's the difference between a force and a dislocation. What I'm going to show you today, though, is that for this dislocation, if I make an assumption, which I'll talk about a little bit later, we're going to actually see a force here. I'm going to kind of perturb the system and see a force in the problem where that force now, which I call a Newtonian force, will be exactly equal to the Peach-Kohler force, which is the configurational force that it's known. I won't go through some of these mathematics, but when you work with dislocations, Eshelby, again, I'm just flashing the equation. Don't worry about what it means. There's something called the energy momentum tensor, which Eshelby came up with, which is a very convenient mathematical way to calculate these forces on point defects. So basically the force, the so-called energetic force, the Eshelby force, is some integral of this weird looking thing. That's all you need to know for now. And again, I'm going to show you that if I look at this perturbed approach, equilibrium approach, I could show that this perturb approach will produce the same result as this variational approach. So let's start here with edge of dislocation in a half plane. This solution is known. If you take the material is actually the orange stuff, there's a dislocation, which is that little T symbol at some distance, lambda from the free surface. The other side is actually air. What you're seeing there is the image dislocation mathematically, but it's one dislocation in the yellow part. That thing, if I surround the free body diagram around the dislocation, there's no net force. It's an equilibrium problem. We're not looking at a dynamic problem. However, that dislocation would want to be ejected from that half plane. It'll want to go shoot to the left because there's an energetic force that drives it to the free surface. The energy looks something like this, and that force in the x direction is 1 over lambda, where lambda is the distance from the free surface. So there's some Eshelby force derived from some variation in energy with respect to the configuration, which is the position of the dislocation. It's there, so that dislocation is feeling a force, even though if you look at the free body diagram around it, there's no applied force to it. So let's do that. I'll do it several ways. The first thing I want to do is, and I think this is the kind of thing that also the faculty here in this department do with new ideas, is you come up with toy problems. So the dislocation is a continuum problem, but let me just give you intuitively what we're doing by what I call a very simple toy problem, where I replace the half plane, if you will, with a bunch of one-dimensional rods that are separated by rollers, so there's no shear stress in that direction or parallel to that direction. And I'm going to produce a dislocation and do some back-of-the-envelope calculation and show you the discrete version of the Peach-Kohler force. So I open it up, right? I open up to introduce the dislocation by the Burger's vector B. Then you stick in that rod. But now remember, this rod now is stuck and keeping these one-dimensional tension compression members separated by these frictionless rollers. Let's see what we get. And the position, again, it's inserted up to a distance c. So the first thing I'll do is I'll use a J integral. I'll use this Eshelby approach of applying this path-independent integral, which I know will be equivalent to the energy release rate, change in energy, and then the derivative will be equal to the force. So we all agree now that that plate that I inserted is only being compressed, right? There's no forces in the x direction, but you'll see there's actually a force that ejects it. Okay, let's see how that works. So if you do the math, you apply the Eshelby energy momentum tensor, you go through this stuff, you get that the force is given. Okay, it takes some algebra, but you could evaluate this discrete version of this so-called Peach-Kohler force. So this force is in the x direction. This thing wants to come out. If you don't keep it in, it's going to come out, right? So again, you're compressing it. No horizontal forces on the bar, but the configurational force is in the x direction. How could I see that now? So let's do it again. You could also look at the energy. We solved that problem again. Just calculate the potential energy in the system, take its derivative, you get the same configurational force again. But the approach that I'm going to be using to try to reconcile the two is the perturbation approach. So what we do is we solve a different problem. Remember, this is inspired by that wall that had that gap. And then I take the gap, I solve the problem, equilibrium with a gap, I take the limit as the gap goes to 0 and see what's left over. So what we do is we perturb the shape of the dislocation so that the multi-value displacement is not a Heaviside function. It has this kind of smooth shape. It doesn't matter which shape you use as long as you could differentiate it and all that, because eventually I'm going to go back to the original configuration. And what I'm going to do now, or what Johnny's going to do, is we evaluate, and again, there's some algebra involved. The right-handed picture, we have this force. We're going to assume, and I'll go back to this, that it's frictionless. That red force is the force on that plate that I stuck in there. And you could break it into the x and y components, right? And then when you take the limit as this thing goes back to that Heaviside function, again, all the math it's easy to do in this particular case. It's a toy problem. When I take the limit, as this thing goes back to the actual dislocation shape, which is that square plate, you get the same force that you got from the Eshelby approach or from the energetic approach. So again, and it's that horizontal component that does not disappear after you solve this equilibrium problem that is driving it out of the half plane. That thing will shoot out like an arrow. If you actually did that experiment, it would shoot out, even though there's no force pushing it out. Okay? And again, you could do this again with the J integral, and you get the same result. You could do it with energies. It doesn't matter how you do it. And again, it's all the same thing, of course, at the end, right? Let me see if I could go here. So now we just generalize this, and I'm going to go through the next few steps relatively quickly. So now we do the dislocation. This solution exists. It's in many different ways you could get this solution. John Dunders has a solution back in the 60s. So the important thing is all the equations are analytic. Okay, we know the formulas for stresses, strains, displacements of all these elasticity problems. So when you take a dislocation in a half plane, we have its energy. You take its derivative with respect to the configuration, and you get the Peach-Kohler force. This is classic dislocation theory. So now how could I get that force, even though, again, I'll say one more time, if I draw a free body diagram around the dislocation, there's no applied force to it. So I do the same thing, or Johnny does the same thing. We take the dislocation itself, which represents that picture on the right. I perturb that shape on its right edge, right? I basically perturb it. And now this is the key. And my last slide is going to be this assumption. Of course, when I now calculate, and everything's analytic, so I could calculate a free body diagram on that shape. But what I do is I neglect the frictional stresses. In other words, when I draw the free body diagram, if I include the whole traction, which is normal and shear stresses, that'll go to 0 when I integrate. But if I neglect the shear and I only include the normal component of the traction, you'll see what we get. So we do that. Again, I'm just flashing these to tell you that we have the analytical formulas. We do the integrations. We get a force. The x component of this force on that dislocation will be the Peach-Kohler force. But now it's visualized in a sort of equilibrium problem where I perturb the shape, I make it go back to the original shape, and I get this force, which again, I call a Newtonian force. But remember, I had to neglect the friction. I'll talk about this later. We don't fully understand that yet. Now we'll do the crack. There's a toy problem in the paper, which I won't go to. Again, we did the toy problem of a crack as this leaf spring system that you could solve very easily with strength of materials, but I won't talk about that today. So let's talk about a crack. Now a crack tip, remember, there's something called material of substance in this language, which was, I think, developed by Morton Girton. A dislocation, in a sense, is a material of substance. You could think of it as that plate. A crack tip doesn't have a material, right? It's a tip. So what we do is we take the limit where we use a cohesive zone model where that crack tip now is going to have some cohesive zone which represents like a block, which I'll show you a picture of, where there's going to be traction on that block, and then I take the limit as I go to original configuration. So the first thing you do with classical fracture mechanics from the course is if you calculate the potential energy change when the crack is moving, you get the J integral again, which is this configurational force. So again, this is just classic results I'm just reproducing. And again, by the way, I didn't mention it, but this J integral is also the stress intensity factor, whatever that is, squared divided by a modulus. So now how do I create a material substance so I could do a free body diagram around it? So we think of it as a cohesive crack, and then we're going to take the limit as the small scale yielding limit of when that cohesive zone goes to 0. So the picture would be something like this. You have a crack. We imagine that near the crack tip, there's this block of material that block is eventually going to become infinitesimally small, and we'll see what's left over. So again, we now take the elasticity solution, the Williams solution of all the stresses, displacements, strains near a crack tip. We apply them to this block, but again, I don't apply the shear component of the traction. I only apply the normal component of the traction. And then I go through all of that, and when I do some calculations, you find that there's a Newtonian force equal to the J integral, which wants to make the crack go forward. So this little block, even though it's infinitesimally small, wants to move forward, right? So this is the picture. It's getting smaller and smaller. See, it gets smaller and smaller, but there's a force. That force is exactly equal to J. So this configurational force, this energy release rate, could be viewed, if I make that assumption about the frictionless block, equal to the J integral. So the last picture of the slide, well, the next to last picture of this talk is how do I visualize a crack the way I explained it now, knowing this. I promise you I won't pull my pants down. That would be pretty embarrassing. But imagine a crack being a zipper, right? If you take a zipper and you look at the tab, you could imagine that a crack is, the analogy would be a toy problem would be a zipper that you pull, right? Right? And what happens? When you pull, the zipper will just move on you, right? That's why sometimes your zippers are broken. It keeps on sliding down. How do you prevent it when you pull on your pants? You basically grab the tab, right? And you hold it, right? Then when you pull on those pants, you're grabbing the tab, so it's not going to go forward, that zipper. But what happens if you pull hard enough, then the amount of frictional resistance between your thumbs and the tab will be overcome, and then the thing will go forward. So think of the resistance as being the fracture toughness. Then the force that you're going to be measuring, I was talking actually to Johnny yesterday, we should do that experiment in the lab. If you numerically evaluate with a load cell the force that you have to hold on to, even though it has different units, you have to figure out how to combine the units between J and F, the value of that force will be the J integral. Okay, that's the idea. So the J integral has this meaning that if under those assumptions, it's like a force, like a Newtonian force. Even though, again, if you draw a free body diagram around the crack tip, the elasticity solution around the crack tip, the net traction has zero force. There's no source of force at the crack tip. So I'm not going to read this. This is the explanation, because the only thing we don't fully understand, but we have an analogy. I wish Roger Fosdick was here today, because he's a fluid mechanician also. You probably explain this to me if what I'm saying makes any sense or not. But here's the idea. The idea is that this is an analogy with fluid mechanics, which Michaela, maybe you could answer this. You know, in one of the great advances to calculate drag on objects in the flow were made by Prandtl, the boundary layer theory, right? In Prandtl's theory, basically, you have this boundary layer between the surface, very, very thin layer compared to other dimensions, where you basically have a zero slip condition, and then you get basically, in the far field, you have a certain field, if you will, that is easy to calculate. You make assumptions in the boundary layer, right, where you have basically some shear stresses which have some variation. There's a constant pressure in the system. What I claim here is that, or what we claim, is that imagine that you have this material of substance. It could be an inclusion like a dislocation or a crack tip, and viewed as a block of cohesive zone. We imagine there's a very thin boundary layer around that material of substance, which again could be the dislocation or crack tip or any inclusion. In fact, the last part of the paper, we do a general Sommeliana dislocation. We show the reviewer wanted to see it not only through the dislocations and the crack tip as examples. He said, we require you to generalize it to a general inclusion, which is what we did. So the idea is the following, is that there's a boundary layer, but it's the complement of the Prandtl, where now you have zero shear in the boundary layer. You have perfect slip at the interface between the object and the boundary layer. In the far field, we have our elasticity solution. So what we're saying is, you could always imagine a solid as being a fluid given enough time, right? It could flow given enough time, so that between the surface of the solid, the material of substance, and the elastic material, you only have this tension compression struts. You have perfectly smooth interface. And if we assume, again, we're trying to understand it even better, that everything we did so far has this interpretation, then you have a Newtonian force, which is equal to the configurational force. And that's the argument we put forth, which is something we still need to think about, by the way, to full disclosure. So with that, hope it was fun.
Do you have any questions for the speaker, for Roberto? Okay, let me open the floor and ask you one question.
Sure.
Isn't this matter of semantics? Because these are essentially, this is the adjoint field.
Yeah, of course. Yeah,
If you
yeah.
minimize any potential,
Yeah.
this is not only a problem, it's the adjoint field where your parameter space is a configuration of the system.
Yeah, I think that's fair enough. I think in general, I would even simplify it. Instead of using, let's say, adjoint, everything's a force, right? Anything that's going to be moving something from one part to another is a force, and we could interpret it through our mechanisms of energies or through this Newtonian approach. So I agree with you in a sense. Ultimately, it's the same thing, but it's, I think, still kind of an interesting way of looking at it, because it's a perturbation, right? In other words, it's clear that if, with this assumption of this boundary layer, right? It's like when you go into the shower, right? If you take a piece of soap, it's dry, you could do anything you want, it's not going to move on you. But if it's wet, you have this very thin layer and you're applying this elastic field, it just shoots out. That's the idea. The question is, if I could buy this interpretation, then I could actually see conceptually a force there, because there is no force around that material of substance. A dislocation does not have a force around it. A crack tip does not have a force. It's an equilibrium. But with this interpretation, you could kind of conceptualize a force. That's the only thing. But I agree with you. It's still ultimately the same thing.
Roberto, nice talk. Thanks for that. With everything except maybe the exception of this last piece, there's singularities in some sense, irregular singularities in the geometry mostly.
Right.
So I wonder, is there an interpretation there where we're sort of applying these ideas outside the applicability of the theory? I mean,
yeah, that's a good
our
question.
Standard elasticity theory is derived without corners.
Yeah.
And we often apply it in problems like that.
Yeah, so, clearly there's no physical singularities, right? We agree with that. I think it was Willis one time said, just because a solution is wrong doesn't mean it cannot be useful, right? So what we do is we assume, well, we could show that if you have a crack, it has a singularity at that point, right, where the crack tip is. But even if you solve let's say, the nonlinear problem, you take care of plasticity, microcracking, there's still a region of dominance where this singular solution applies. If you actually evaluate the stresses out there, as long as the zone where it doesn't apply is big enough, too big, then those fields are good. I think precisely because near that crack tip, we cannot really describe things to the levels, because it's not realistic. It gives actually credence to this idea. We use the idea of boundary layer in fracture mechanics to say that at a distance away, we have this region which is dominated by the K field. And what's happening here, we kind of avoid it. And so just like we said, well, we have plasticity there, that thing. What is happening near the crack tip? Could it be that we should allow that degree of freedom, sort of a shearless degree of freedom? Because remember, I'm using elasticity only out here, nowhere in here. That's the idea. So that was the idea that we had of interpreting it a la Prandtl, because we're going to avoid that region anyway. So the same way we allow ourselves to accept singularities away, we're allowing ourselves this assumption of frictionless by saying, okay, well, I could do whatever I want in there. Believable or not, I don't know. We're still trying to understand, though, this thing here. This is really something we don't fully understand. Yeah, Michele. Yeah, sure.
Just briefly. So, I mean, what about the possibility of saying, well, when there's a sharp corner in the geometry, we need to enrich the theory with a force at that corner.
Yeah, that would be an approach. Yeah, we could also do that. Absolutely. Yeah.
Just a question.
Well, yeah. So what you're saying, in a sense, right? I'm not trying to put words in your mouth, you're perturbing this geometry, right? Like you said, you could change the geometry near the corrective.
Brings you back to the theory that is rigorous.
Yeah, because that's what this is doing in a sense. I think what you're doing, if I'm interpreting your question, when we do this, that's kind of, in a sense, we're not keeping that singularity, right?
Right.
We're perturbing it, yeah. So we're perturbing it geometrically, but again, in the microstructure, you never see a sharp crack. Right? There's always some blunting and some rich geometric structure unless you're cleaving a crystal. Sorry, Michele, yeah.
Just a question on the analogy with the boundary layer. So in the boundary layer theory, you have the depth of the boundary layer, which depends on the Reynolds number.
Right.
With some, I guess, is 1 over the square root of it. So in fact, it would depend on an outer scale.
Yeah.
And do you need that dependency there?
Yeah.
So do you need mathematically the
Yeah.
dependency on the size of the inclusion?
Yeah, I agree. So I think that if this was worth pursuing, we would actually solve a different problem, right? Not just the elasticity problem. We would solve some viscoelastic fluid type problem, incorporate all those non-dimensional variables, take the limiting scales, and see if we see similar things. That's what you're saying, right? It's like actually solving it in a rigorous mathematical framework within a constitutive equation.
Yeah, essentially I was wondering if this is just a buffer layer or if it's a buffer layer with the dependency on the size of the inclusion that will, in that case, will be more kind of consistent with the analogy of a boundary layer and the Reynolds number dependency.
Yeah, I agree with that. So what we're saying now is, because we have a good feeling for cracks, is when you look at this last picture that we have, so, this zone clearly, same as a fluid, what is it like? The fluid, it's, you want to achieve 99% of the flow in the outside, right? So basically, the idea is it's very, very small, so small that I could apply to transmit through this zone the elastic field, right? That's the idea, which is analogous to you have your simple flow out here, right? Your shear flow, whatever. And then in here you have certain assumptions that you solve inside. And so the equivalent would be that this would be the drag force, right? But it's complete opposite. Yeah. We have perfect slip instead of no slip, and we have zero shear instead of shear. That's the idea.
Thank you.
Or it could all be nonsense.
I just want to restate maybe in a slightly different way what you said. I think in the sense that we simplify the geometry to a point that we lose we cannot see the Newtonian force anymore, and you can only look at it from an energetic point of view.
Absolutely.
All the problem that you have shown is that. No?
Absolutely. I agree with you 100%, Emmanuel. That's a perfect way of saying it. What I like at Emmanuel is I could talk for 30 minutes and he'll say in 10 seconds the real essence.
Hi, Roberto. Very nice talk. I wonder if you consider the elastic medium around the crack has some spatial randomness.
Say it again.
The elastic medium, elastic modulus, for example, around the crack tip has randomness spatially. Then this configuration force should have some randomness as well. Yeah. Does that can be captured by J integral? Is J integral path dependent in that sense?
If the J integral the J integral is only path independent. Ultimately, if there is no what's called explicit derivative, you cannot have a strain energy that's dependent on the position of the crack tip.
But if let's say the elastic medium has a randomness in Young's modulus, for example.
I don't think it would be path independent only because if I think of the elastic prop, if I take a crack and you vary the modulus in this direction, it'll be path independent. But if you vary it in this direction, it will not be independent. So if you think of the micro cracking as changing spatially in this direction, the elastic modulus, that it cannot be path independent.
So which path you would choose to determine
Well, you wouldn't use a
randomness?
J-integral in that approach. You simply cannot use, in general, you don't use a J-integral if it's not an application where it's path independent.
Okay.
Now, there may be ways of patching things up and looking at inner and outer and coming up with some physical model, but generally speaking, if you actually look at the derivation, which is not in most books, it's only in the book on molecular dynamics by, who's the guy at Caltech that used to be at Brown? Anyway, is when you look at all these energies, there's what's called explicit, if you take the strain energy, we always say it's a function of strain, right? But there are configurations where the strain energy is also a function of the position of that crack tip or dislocation. When you're taking the derivatives to prove the path independence of the J-integral, they always do the cases where there's no dependence on that coordinate, and that's why it's path independent. If you have a dislocation in a half plane, the strain energy will depend on the position of that dislocation. And so that's where that force is coming from. It's that explicit derivative. Yeah, so all these materials, yeah, the question is whether I've taken into consideration different types of materials. All these theories are for linear elastic materials. These are all linear elastic materials. And by the way, going back to what Emmanuel said, the whole idea of energies, it's a very good way of doing things when things are very complicated, right? I mean, whether it's dynamics, problem, whatever, that's why we use them, you know, this idea, Hamiltonians, whatever. There some problems you cannot deal in any other way by energetically. So if I were to lean, I'd lean towards energy approaches because, sometimes you just can't deal with those details, or those details may violate some of that approach, but the energies are captured, right? You could capture things quite well with energies.
I believe that we have some questions from the online audience. One is from Roger Fosdick. He says, perhaps the shear stress is absorbed into surface tension in the surface that is developed and balanced.
Thank you, Roger. I agree. So Professor Fosdick, which I mentioned, I didn't know he was on Zoom, basically said, if you heard what he said, is that perhaps the shear stress, which I'm sort of neglecting in the calculation, could be being absorbed in that boundary layer, essentially. So it's transferred through there in a different way. Thank you, Roger.
Any other questions?
Thanks, very nice presentation. I just want to know, for instance, what happens, for instance, if you have more than one crack, perhaps.
More than one crack? Okay.
Yeah, perturbating the medium and also probably interacting one to each other. How do you treat in this condition?
You mean, so the question is if there's multiple cracks?
Yes, if they interacting or
them?
Perturbating the medium somehow.
Oh, no. I wouldn't do this exercise on a bunch of cracks. We're just trying to show what would happen with one dislocation or one crack tip or one inclusion. If you have multiple cracks in the system, first of all, we wouldn't have any analytic solutions that I could even do that exercise, right? You would have to solve those computationally. But we do solve multiple crack problems in general to see how structures interact with each other, like that seashell that has many cracks, right? We showed that one of the toughening mechanisms is the shell actually grows. It's almost like doing Ali's rope-a-dope. It becomes hit. So when the shell grows, it creates these surfaces at growth, which are basically glue. But that glue is very weak. And you say, why would it grow these parallel sheets of aragonite glued by this very weak? Why? Because it wants it to crack. Because when it cracks, those cracks stop at this tough interface, and instead of one growing, one cracks, then another one cracks, and then others crack, and you're creating more and more surfaces. And creating surfaces is a toughening mechanism. So this shell, one of the mechanisms, in that particular example, you could toughen that shell by about a factor of 100 by just that microcracking. Then there's other mechanisms also. So that's an example of a multiple crack problem. And that's it's a beautiful homework for fracture when you use the J integral to calculate the J. It's not mine, by the way. That's in Hutchinson's book on nonlinear fracture from like 40-something years ago. It's one of the exercises. Cracks have been good to me. They allow me to travel back to one of my homes, right?
Any more questions? There's none more online, so if there are no more questions, please join me in thanking Roberto one more time for the delightful lecture.